Hello everyone. Today we'll be looking at the area between two curves, and we'll be looking at what we mean by the area problem, an area formula, and we'll look at a basic example of how to find the area between two curves. So the area problem can easily be stated as such. Suppose that in some interval from a to b, f and g are continuous functions and that f of x is bigger than or equal to g of x. How do we find the area of the region bounded by these two curves on the interval? So if we get ourselves a function to look at, and f of x is bigger than or equal to g of x, which means that this top function here, that's our f of x, and that bottom function here, that is our g of x. And we want to try and figure out how do we determine the area of the region enclosed or bounded by these two curves on that interval. So we'll take ourselves some interval, let's say from A to B. And if we look to try and approximate this, we could probably approximate it fairly closely using a rectangle. That's pretty common for us. And if we're here at some random point x sub I, the width of that rectangle is what we call delta x sub I, and you could see here that that height there is just the difference of the upper curve f of x minus the lower curve g of x. So our area could be approximated with this Riemann sum here, where whatever your favorite index is, we'll just sum over the area of each of these rectangles, which each has height of f of x sub I minus g of x sub I. And each one has a base of delta x sub I. Well, we've seen something like this before, and we know that if we take the limit as delta x sub I goes to 0, that this here then turns into an integral over the interval from A to B. So that turns out to be exactly how we define our area. So the area of the region bounded above by the curve f of x and below by the curve g of x, on the left by the line x equals a, and on the right by the line x equals b, is given by that formula there. And that right there, folks, is the area we've been looking for. So let's see how this is going to work in an example. So let's find the area of the region that is enclosed between the curves y equals x squared and y equals 6 minus x. Now they use the phrase enclosed between. And since they didn't give us two vertical lines on the left or the right, it's probably a safe assumption that these two curves somehow enclose, pinch off an area. So let's draw these two curves. So y equals x squared is an opening up parabola. And y equals 6 minus x, now I just need to sketch, is a line with a y-intercept of 6 and sloping downward. So we could see that we have 2 points of intersection, and that the area we're looking for that's enclosed actually truly is enclosed. It's right there. That sort of cut bowl looking shape. Now we need to find these 2 points here. because that's going to be the start and the end of our integral. And so in order to do that, we'll just set our two equations equal to each other. And solve. So that's a pretty simple quadratic equation. So x squared, if we move everybody to the same side, plus x minus 6 is equal to 0. And then if I factor this factors into x plus 3 times x minus 2, and I could see that the 2 points where my curves intersect are at x equaling 3 and x equaling 2. X equaling negative 3 and x equaling 2. So those are going to be the bounds on my integral. So let's compute our integral now. And so our area is just going to be the integral from negative 3 to 2 of the upper curve, which was the line 6 minus x, minus the lower curve, which was the parabola x squared, and that integral is with respect to x. If I just rewrite this in sort of standard order, so negative x squared minus x plus 6, and there isn't necessarily a need. And then each of these, if I just apply my power rule, so I'll add 1 to the power and divide by the new power. So the integral's been dropped. So I'll just apply my power rule. So add 1 to the power and divide by the new power. So that's negative x cubed over 3 minus x squared over 2 plus 6x. And I'll just evaluate that on my bounds of negative 3 to 2. So let's see what that gives us. So if I plug in 2 first using the fundamental theorem, so I plug in the upper bound, I get negative 8/3 minus 2 squared over 2, that's 4 over 2, plus 6 times 2, which is 12. And that is going to be minus, if I plug in negative 3, so negative 3 cubed is negative 27 with another minus sign, so that's 27 over 3, minus negative 3 squared over 2, which is minus 9 halves, and then last but not least, plus 6 times negative 3, which is negative 18. And if we simplify all that and add up all those terms up using your calculator, in the end you get 20.56, or if you're an improper fraction person, 125 over 6. So either one of those is acceptable. And that's the amount of area enclosed by those two curves. So that concludes our video on the area between two curves, where we looked at the area problem. We were able to derive or define an area formula, and where we looked at a first example to see how it's done. So thank you very much, and have a wonderful rest of your day.